I would like to make some other points in terms of, let's say, many-body machinery for coupled cluster theory before going to like an overview of more recent results in terms of ground state energies, radii, neutron skins, polarizabilities that can be relevant for astrophysics applications. So, yesterday, I showed you the CCSD amplitudes. We understood that we have a lot of unknowns here. We have a very big set of algebraic equations to solve. But to actually calculate these equations, as you can see there, we need these matrix elements of the similarity transformed Hamiltonian. So we need to understand how to calculate this similarity transformed Hamiltonian. And the way to calculate the similarity transformed Hamiltonian is to use this expansion, which is called Baker-Campbell-Hausdorff expansion, BCH for friends. And you can actually show as an exercise, if you have if one evening you're bored, you can show that actually if you take the definition of the similarity transformed Hamiltonian, you can actually show that this equation is valid. So, and one thing that this BCH expansion is actually useful for is that when we deal with a two-body Hamiltonian, but we could generalize also to the case of a three-body Hamiltonian, the expansion is truncated, it truncates naturally at fourfold nested commutators. If we have a three-body Hamiltonian here, it will be truncated at six-fold nested commutators. And so, why? I will show you, let's say, try to give you an idea of why this happens, why this is important, and why this is an advantage with respect to other many-body methods. So, let's keep things simple. And so we can start, okay, we have the similarity transformed Hamiltonian, which is equal to our normal ordered Hamiltonian plus like a first commutator, so this HNT. And so we can just start from this term. So if we just expand it, we will have HNT minus THN. And so here we can actually apply the Wick theorem. And so we can, okay, say we normal order each of the terms. So we will have normal ordering acting on HNT. So remind, Hn is a two-body operator, so it's basically sum over strings of annihilation and creation operators. The same also the cluster operator. So also in that we have strings of annihilation and creation operators. We can put them together and normal order them. And then we have contractions. So we will have a terms that looks like this, with which I indicated the possible contractions that we can have, taking into account the annihilation and creations operator that are here. And then we have the THN term. And it will be the same thing. So THN minus, and also here we will have contractions. So if we normal order this, and if we normal order this, we will get the same result. So these two are basically going away. And so we just are left with these contraction terms. So let's remind a bit what is exactly inside Hn and what is exactly inside T. We in fact know that only certain types of contractions are actually different from 0, and so they are actually contributing when we look at the contractions within these operators. So in the case of Hn, we have that in our second quantization form, we are summing over all particle and all states. So we don't have any kind of restrictions there. But in the case of T, we are just considering terms like A daga A, AI, or A daga A daga B, AJ, AI. So we only have pseudo-creation operators that are entering here. And so we have to, and so like the only non-zero contractions that we can have inside these operators are actually coming only from terms in which we have contractions like AI, AJ, we know that this is delta IJ, or AA, AB dagger, and this is delta AB, okay? And so if we have Tn T coming first, we will have that actually only terms like this are in front. And so we have only these A dagger A dagger B, only particle operators that come first here. And so this term, in the end, will actually not contribute because we have that only these operators are in front. And then we have to consider, and so in the end, what actually happens is that only terms in which H lies on the left with respect to T will actually contribute. So we will have this. And this comes, let's say, you can generalize this reasoning also for like the more complicated commutators that we have inside the BCH expansion. So this happens because T has a specific form. T depends only on pseudo-creation operators. And this also determines the fact that our similarity transformed Hamiltonian is non-Hermitian. Now, let's think about the case in which T is instead unitary. What happens? Do we still have this? Is someone brave enough to try to give an answer? No? Why not? Yeah. So, like, okay, let's think about it. So if we have a unitary transformation, if we want to make our similarity transformation e to the minus t hn e to the t unitary, we need to have a unitary operator here. And so we can think about something like t minus t dagger. And we saw, like yesterday, I think I showed that T dagger is actually a de-excitation operator. So we will have that here, terms like AI dagger A, or A dagger J, A dagger I, AB, AI, well, okay. We have to switch the indices. But okay, terms like this are also contribute if we take into account this T dagger. And so in the end, it means that if this similarity transformation is unitary, we don't have this nice feature for which this term actually goes to 0. And so it means that if we have a unitary similarity transformation, this BCH expansion will not truncate at 4-fold nested commutators if we have a 2-body operator, or 6-fold nested commutators if we have a 3-body operator. It will just go on up to infinity, and so we will have to truncate it in an artificial way. We have to introduce a truncation. And actually, there are methods like the medium similarity renormalization group that I will introduce a bit later, where actually this happens. They have a formalism in which they perform a similarity transformation of the Hamiltonian, which is unitary. And so they have to truncate the BCH expansion at a certain point, while in coupled cluster, this happens naturally. So is this clear? Do you have questions? Yes. Yes, you can also interpret that as acting with a unitary transformation on your Hamiltonian. Basically, you are applying to your Hamiltonian a unitary transformation in such a way that you will get basically a diagonal Hamiltonian. It will decouple your reference state from your excited states. You can see it also in this way. So yes, so they have a similar thing, which is called Magnus expansion, and they, instead of having it truncated naturally, as it happens in coupled clusters, simply they say, okay, we will retain up to 2 body operators, up to 3 body operators, etc. So it's an additional truncation that comes in the many-body method, because such an expansion does not truncate naturally. Other questions? Good. So we can go on from here. Okay, ground state energies. So we wanna. Okay, this is still not working. So I will stay down here. So ground state energies, this is the first fundamental observable that we would like to test when we develop a many-body method. Are we able to actually get the energy of the ground state? Oh, okay. Like this, I have to. Yes, it says the laser is working, but the slides are not going. Yeah. Okay, I will just stay here next to the PC. So, okay, ground state energies. So this is the first observable that we want to look at and we want to test, let's say. So let's start small. So when you want to test a many-body method, always, let's say, reduce the problem to like the light system you can do. And so here you see results for the ground state energy of helium-4 using coupled cluster singles and doubles, and singles, doubles, and triples. This is another different approximation for triples that we can actually use. It's called like perturbative triples. This is like, it's not important exactly what it is. The only important thing is we are adding some triples contribution to our result. And then we compare it with exact results from Fadeev-Yakubovsky for a certain interaction. And here you can actually see also the convergence of the ground state energy of helium-4 with respect to Nmax, so with respect to the number of major oscillator shells that we have in our system. And actually we see that first, CCSD actually is able to get a lot of the correlation energy already, and with triples we actually get exactly on top of experiment. So this is very good. We can go beyond that, we can go to oxygen. This is like a figure that also Ingo showed in his presentation. Is a good benchmark with all methods regarding the ground state energies along the oxygen chain. And in particular, we can also look at the effect of three-body forces. This is something that we see also in coupled clusters. So if we add three-body forces, we are actually able to get the right drip line along the oxygen chain. And another result, which I think then will be also presented by Nakamura-san, is the first observation of oxygen-28. So oxygen-28 is like if we just naively put the 28 particles into the shell model, this is actually a closed shell nucleus. So it's important to actually test if this is an unbound system. It's a strong test of our understanding of nuclear structure. And so here you see the experimental data for the ground state energy relative to oxygen-24 of oxygen-28. This is the last point. You see that this plot is a function of neutron number. So this last point is actually the prediction for the ground state energy of oxygen-28, which is slightly higher with respect to 0. So it is unbound with respect to oxygen-24. We have here actually a bunch of different theoretical calculations, some ab initio, some of them are, I think, shell model. And you see that they predict a slightly higher ground state energy for oxygen-28, but they are almost all in agreement in predicting an unbound oxygen-28. So this is, let's say, an important test of our understanding of nuclear structure in the oxygen chain. And yes, yeah. Yeah. So like here we just predict, let's say, what we just calculate, let's say, the ground state energy as I showed before. So like just solving our couple cluster equations and looking at what is the lowest state that we get. And with, no, it can also be unbound. We cannot say with this calculation if it is a resonance or not. We just get the position of the state. We can look at what is the contribution of triples, for example, but in this specific calculation, we can't say if it is a resonance. We don't calculate the width in this sense. So we have an uncertainty which is dictated by our nuclear interaction and by our many-body method, but we do not predict the actual width of the state.
But the wave function is always composed by the harmonic oscillator's wave function.
Yes. Like we start from, it's not harmonic oscillator, it's an R3-Fock. Basis, because we start from the harmonic oscillator, but then...
But you have no states in the continuum.
No, I don't have states in the continuum. But I can still get the separation energy. I can still get the excitation energy of oxygen-28 with respect to oxygen-24, but I don't have the actual width. Yeah. Yes. And we can also go heavier. And we can also go heavier and go in the calcium chain. This is the same plot as I showed before in the case of oxygen. So we see what happens when we just consider 2 body forces, and then we also add 3 body forces. And we actually see that this is crucial in order to get on top of the experimental data, and also the drip line that we predict if we include three body forces here is different with respect to what we would get without them. Radii. So how do we actually calculate radii? So this is actually something that it's a bit more complicated by the fact that we need by the fact that we are dealing with a similarity transformation of the Hamiltonian, which is non-Hermitian. So when we consider the expectation value of a certain operator on the ground state, but it can also be on excited states, we have that our similarity transform Hamiltonian is non-Hermitian. So the main consequence of this is that we will have right and left eigenstates which are different from each other. And so this means that we have to do two calculations. We need to determine the right eigenstate of Hn and also the left eigenstate. So we have right wing and left wing, and we have to put them together, which is always very difficult, but okay. Art of compromise. So, the simplest thing is actually the right eigenstate, because as I showed you yesterday, the Schrödinger equation that we are solving is this one here. So the right eigenstate of the similarity transformation actually correspond to our reference state. And so, okay, we are happy. We have the right part. We still have to model the left eigenstate of Hn. And so a way to do that is to say, okay, my left reference, so my left ground state, will be given by the action of a de-excitation operator on top of my reference state. And in particular, this de-excitation operator is kind of modeled in the same way as our cluster operator, but it is basically its adjoint. So here, instead of having, as I was showing before, where is the, okay. So as I was saying before, so in T and T dagger, we have these terms. Instead, in the case of lambda, we will have this, instead of having the pseudo-creation operators, we will have the pseudo-annihilation operators. And so this means we are actually de-exciting our system. So we will have terms that goes in this way. And so when we actually calculate an expectation value in coupled cluster, we need to perform two truncations. One is on the right side, and one is on the left side. And so we usually take them for consistency as the same. So if you want to work at CCSD, one will calculate, we solve the equations at the CCSD equations for the left and for the right state. And so in this case, so one can then write the expectation value as, let's say, the expectation value of the operator. I use two different notations. I'm sorry for this. But O and theta are the same thing. I'm sorry. And so here we have the left ground state, the right ground state. This will be our ansatz for the left ground state, which will be a bit more complicated, and then the usual coupled cluster ansatz for the right ground state. And this is our final expression, that is the actual one that we will use when we are interested in expectation values. Okay. Also here, we start from a benchmark with different methods. This is actually like a recent paper in which experimentalists have measured charge radii along the nickel chain. And what you see in these two plots is on top, we actually have the experimental data are in black, the coupled cluster predictions are in red, and then we have other two ab-initio methods, valence space MSRG and self-consistent green function with the other two colors. They all use one specific chiral interaction. This chiral interaction is kind of special with respect to others because usually nuclear interactions are fitted on light nuclei data. So like N scattering, phase shifts, as also Ingo was mentioning, and few body data. We don't go beyond maybe helium-4. But in the case of NNLOSAT, in the fitting, the optimization also contained data from oxygen and carbon. So there is medium mass information into this interaction. And you can actually see that the predictions of theory are in very good agreement with experiment. This shows that we are understanding, let's say, the physics of the charge radii along this isotopic chain. Here, they're also considering the difference of the charge radius with respect to a reference isotope, with respect to nickel-60. So here you actually see that at 60 we are at 0 for this reason. And also here it looks like theory is doing a pretty good job. But some challenges actually remain. So here I'm actually looking at charge radii in the calcium chain. This is an experiment that was done in 2016. They measured the charge radii of calcium-50 and calcium-52 with laser spectroscopy. And so here you see in color, you have different predictions from theory using different nuclear interactions. And then in black, you have the experimental data along the experimental data that are available along this isotopic chain. You actually see that in general, the trend is reproduced. So the interactions are actually following the trend of the theory. The only problem is that the kinks are not, let's say, enough pronounced with respect to what happens with respect to what happens in experiment. In fact, the actual problem lies in the differences of. So if we have like a difference between calcium-48 and calcium-52 given by experiment, which is up here, you see that, okay, ab-initio is actually a coupled cluster here. So you see that all the interactions which are used are actually predicting like a lower difference, so less pronounced kink. DFT also predicts a lower value for this differential charge radius, and the same also for configuration interaction. So we can actually see that this is kind of a problem which is seen by different theoretical approaches. Actually, also other methods are struggling with radii in calcium. And in particular here, I wanted to just say a few words regarding the medium similarity renormalization group, because this is something that came up yesterday. So the idea of this method is actually to perform, as I was saying before, a unitary transformation of the Hamiltonian that allow us to decouple the Slater determinant, the reference Slater determinant, by all the other excited Slater determinants. So we will have a situation in which, let's say, the overlap between the reference and the other excited states is basically 0. So we want to get here in such a way that then we can extract from here our correlation energy. And so idea, decouple reference state from excitations using a unitary transformation in this case. This is nice when we calculate then expectation values, because we don't have to deal with differences on the left and on the right side. But in this case, as I was saying before, our BCH expansion actually does not truncate. And this same idea, in the case of the E-medium SRG, can also be applied to open shell nuclei. So And this leads to the valence space IMSRG. So the idea here is that instead of decoupling the reference from the Slater determinants, we will have a decoupling between a core, a valence space. So as I was saying yesterday, if you're interested in, I don't know, silicon-30, we take a core which can be, for example, oxygen-16. A valence, which will be like all the shells that go from oxygen-16 up to silicon-30, and then we will have an outside space. And in general, all of them are coupled in our Hamiltonian. And then via the similarity transformation evolution, we can actually decouple these different components, and in this way we can extract an effective interaction that we can put into a shell model code, and that we can diagonalize it and get all the properties of and get all the properties of nuclei from that shell model diagonalization. And this is the result for radii in calcium by the valence space IMSRG. So here we are considering differential radii between calcium-48 and calcium-52. So you see here the, let's say, equivalent basically of CCSD. We are not able to get to the experimental data, which is up here, while all these points are instead like different interactions. So dependence on the Hamiltonian is not helping us here. We have to go, this is not actually the problem. And here they tried to include in their framework also some triples excitation. So you can see this as kind of an equivalent of our CCSDT1. And so you see that in this case, for a specific interaction, actually nothing changes, almost nothing changes with respect to the difference in radii. So this is still, let's say, an open problem in nuclear structure. Okay, let's go to calcium-48. So this is actually a work that was done in 2016. There was a study with different nuclear interactions, so different using coupled cluster and also density functional theory. The idea was to explore correlations in radii and then use those in order to obtain constraints for nuclear matter. So here you see the point proton radius of calcium-48. There is a very precise value available for it. And so if we plot the point proton radius as a function of the skin and as a function of the neutron radius, we can actually exploit the correlation that we obtain in theory in order to obtain a prediction for the skin and obtain a prediction for the neutron radius. In particular, the crosses that you see are coming from ab-initio, so they're coming from coupled cluster theory. The diamonds instead are coming from energy density functionals. And we actually see that the correlation coming from ab-initio data is preferring lower values of the neutron skin with respect, for example, to what we see from energy density functionals. And this is actually, and you can think about energy density functional as kind of an enhanced mean field approach. And in that case, what we notice is that there are some shortcomings in describing the properties of closed shell nuclei, and this is actually what we are seeing here. So look just at the value of the neutron skin. It looks like it is between like 0.12 and 0.15. So actually later on, the CIREX collaboration performed a measurement of the neutron skin of lead-208. So as also Nakamura-san was pointing out, the measurement of neutron-related properties is way more difficult with respect to proton-related properties, obviously because of the presence of the electromagnetic interaction that is helping us for charge radii, but for neutron radii, this is not the case. And so what we can do is to explore this using hadronic probes. But when we use hadronic probes, we actually have to deal with the strong interaction when we analyze the data. And so we introduce errors, because in that case, obviously, the reaction calculation is using some approximation. So it would be better to actually find a probe of the neutron skin, which rely on the electroweak interaction, which we understand better. And this is actually the point of the CIREX experiment. This is a parity-violating elastic electron scattering experiment. What does this mean? So the idea is that we want to, we just take some electrons and we made them scatter against calcium-48. Instead of just and while doing this, we perform a measurement in which we perform two measurements, actually. A measurement in which the electrons are polarized in a certain direction, and a measurement in which the electrons are polarized in a different direction. And due to the fact that the weak interaction is actually breaking parity, we will have kind of an asymmetry coming out when we compare the cross-sections that we obtain with a certain polarization and the cross-section that we obtain with the opposite polarization. And via some theoretical calculation, what one can show is that this parity-violating asymmetry is actually connected to the weak form factor of the nucleus. And this is a quantity that is related then to the neutron skin via theoretical models. In this case, DFT, energy density functional theory models, are used. So when we, from the experiment, we get this quantity, we get the parity violating asymmetry. From that, we can get this weak form factor, and from it, via theory, we get the neutron skin. So still, there are some approximations along the way. But let's say, it's at the moment, let's say, considered as one of the probably most reliable ways of extracting the neutron skin. And so from the experiment, we actually get that this is like the neutron skin is around 0.12, which is actually in very good agreement with ab-initio data. So we actually get that the neutron skin of lead is kind of lower. So, and from the radii in calcium, we can actually get to constraints on nuclear matter, and in particular on the symmetry energy parameters that we mentioned at the beginning. So in the work that I was mentioning before on 2016, what they did was to study the correlation between these parameters that one can get via nuclear matter calculations and the point proton radius, which we know very well experimentally. We obtain a correlation that we can then use to obtain constraints on J and L. And as you can see here, you obtain a J which is, let's say, around 30 MeV, and a value of L which is between like 35 and 45, more or less. But let's say below 50 MeV. Actually, this is, let's say, not really in agreement with another experiment, which is instead focusing on the case of lead-208. So the measured neutron skin of lead-208, again using parity-violating elastic electron scattering experiments, is suggesting a larger value of the slope parameter with respect to previous constraints. So here you see like the same figure as before, which relates, let's say, the parity-violating asymmetry with the neutron skin. And as you can see, this is done via a series of energy density functional predictions for this quantity. And if we translate this value for the neutron skin into constraints on the symmetry energy parameters, so L and J, we actually notice that the value for L is way higher with respect to the one we were seeing before. So from like the ab-initio calculations in calcium-48, for example, we were getting something below 50 MeV. Here, like the central value is around 100 MeV. However, like it's important to take into account that this prediction is only given by this experiment. Also, it has big uncertainties. And if we look at other constraints coming from different sources, we have a mild tension. This is what we can say. Okay. So very recently, in 2022, for the first time, ab-initio calculation got also to lead-208. And here you can see the prediction for the neutron skin of lead-208, which is given by this distribution here, in comparison with different experiments for measuring the neutron skin of lead-208, different constraints, let's say, coming also from astrophysical observations. So here is our distribution with the 68% confidence level here in black. And then you see the Pyrex one is the purple result, and it's actually, yes, kind of in mild tension with respect to the ab-initio prediction. It's around 1.5 sigma. Then we have results from hadronic probes, and we have also, so like this can be, for example, proton scattering. And then we have also results from this pi-zero photoproduction. This is another possible way of actually getting to the neutron skin via, again, hadronic probes. And then here we have the constraint that comes from gravitational waves. So in general, we see the constraints on the neutron skin of lead-208 are kind of lower with respect to Pyrex. So there is a mild tension here. They kind of prefer softer equation of states with respect to the Pyrex prediction. And using, let's say, the set of interactions that was used in this work, we can actually get, again, constraints on the symmetry energy at saturation density and the slope parameter. And actually, here you still see lower values with respect to the one that we saw from Pyrex. So actually, in general, if we make a plot putting, let's say, all the constraints we have at the moment for the neutron skin of lead-208 and the neutron skin of calcium-48, we can actually see here ab-initio prediction are kind of favoring a lower neutron skin with respect to Pyrex, more in agreement with other experiments, also in agreement with the constraints from NICER, from the GW170817, so like gravitational waves. And this is a work that actually was done by Ingo as well. And it comes from the non-parametric model of the EOS he was mentioning yesterday, and constrained by chiral EFT and astrophysical observations. And so in general, we are kind of in mild tension with P-rex. There is also like a theoretical prediction coming from this dispersive optical model, which is favoring instead larger value of P-rex. But at the moment, this is kind of an open problem, and we are waiting for the next experiment that will be done in mice probably in a few years to actually maybe get a more precise value for the neutron skin of lead-208. In the case of calcium-48, actually, we have kind of the opposite situation. Usually, like, calculations are favoring lower values of the skin. Here we have some predictions are kind of higher with respect to the C-rex result, but in general, the agreement is pretty good. For example, if we take energy density functional theory, they will have an hard time putting P-rex and C-rex together. As you were seeing before, in fact, like the density functional theory results, they were all favoring larger values of the neutron skin for calcium-48. Okay. Excited states. So how do we do excited states in coupled cluster theory? I showed you how to calculate ground state, how to calculate excited states of the Hamiltonian. Here, we would like also to calculate arbitrary excited states of our system. And what we do here is to make an additional ansatz. So in this case, we say, OK, our excited state will be the action over the ground state of a certain excitation operator. And this excitation operator can actually be written in the same way as the cluster operator. And so at this point, what we say is, OK, how can we solve for these amplitudes that come out into this operator? And actually, there is a difference with respect to the form of the operator in the cluster operator and in this EOM formalism. We see that there is this constant here coming out at 0th order. So when is actually this constant different from 0? Think about the fact that here, like if we have like a spherical nucleus, it will have a ground state which is 0 plus. If we are considering an excited state, it will have a different angular momentum. If we are not considering, obviously, excitations which are like 0 plus excited states. So when is actually this term contributing to the expansion when it is different from 0? So if you just look at this expression, so at the equation of motion ansatz, you see that psi 0 should be 0 plus. Let's constrain ourselves to the case of like a spherical nucleus. So this should be 0 plus. And this, we know, has a different angular momentum. Or it can be 0 plus if we are looking for excited states of 0 plus nature. So in the case in which this has a different angular momentum, since R0 is only a constant, these two cannot be connected. While in the case of having a 0 plus excited state, we can connect these two. And so we will have that R0 can be also different from 0. Is it clear? Yes? Is a constant, yes. Exactly. So it's so R0 is a constant, and then you have all the string, like the pseudo creation strings contributions, but R0 itself is only a constant. Exactly, exactly. And so, but this normalization will be there when actually we have that these two states have the same angular momentum. Otherwise, otherwise we will have just that R0 is equal to 0 because we cannot connect these two via constant. Yes? So like in the case in which it is 0 plus, we can, for example, connect them with like an R square. And so in that case, still we can have here maybe a 1, like a normalization of our ground state. But it doesn't actually, like you have additional contributions then. That's not your only contribution to the excited state. So this will, like, in the limit in which you get to A particle A also, obviously you will have like the exact orthogonality between the two states. However, if you like if you just consider the constant, that's not a good approximation of the state, obviously.
So you say the other weights will be such that will cancel the when you contact psi mu with psi mu.
Yes, so here we will have...
In the case of the same angular momentum.
Yes, in the case of the same angular momentum, we will have that this is basically a normalization. But then we have additional contributions that then are building up our excited state. Yes. So let's see what happens when we actually put these ansatz into the Schrödinger equation. Okay. So let's take the Schrödinger equation up there. So Hn psi mu equal to delta E mu psi mu. So we put into that the ansatz that we have. So psi mu will be the action of an excitation operator on top of our ground state. In coupled cluster, we write the ground state as e to the t psi 0. So at this point, as we did before for the case of the ground state, we can multiply from the left with e to the minus t. So we will have e to the minus t, hn, r mu, e to the t, psi 0, delta E mu, e to the minus t, r mu, e to the t, psi 0. And then we can rewrite this in terms of the similarity transformed Hamiltonian. And we will get this equation. In terms of the reference, which is what we are, which is like the way in which we also write the ground state equation. So, what did I do in going from here to here? There is something that I did which is not exactly immediate. What? Why do they commute? Exactly. So they have the state structure, they commute, and so we can write the equation in this way. And this is actually what is shown here. OK, so before going to all the other results, do you have questions on? Yes. Right point. So here, no. This is not the this is not with respect to the ground state. So the way in which we write the Schrödinger equation for coupled cluster for the ground state is in terms of the correlation energy with respect to the reference, the HF reference. And here we actually do the same. So this delta mu, this is actually a good point, is the excitation energy of the state we are looking at with respect to the reference. We can then rewrite, let's say, this equation also in terms of the excitation energy with respect to the ground state. Yes. Yes. No, no. Yes. Mm. Yes. That's the coupled cluster. That's the coupled cluster ansatz. We assume the nuclear. Yes, yes. It's the ground state that we. It's the coupled cluster ground state. Obviously, it's not the exact one because we have truncations in it. It's a good approximation. Yes, it's the ansatz, the coupled cluster ansatz, for the ground state, the usual exponential ansatz.
So you say if you apply HM to psi naught, you are going to have energy times psi naught plus some small terms that says remaining terms that says that psi naught is not the exact.
No, 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 no. The fact that it's not the exact thing is given by the fact that here this T is truncated. So it's not, does not get to a particle a hole, it gets up to 2 particle 2 holes, so 3 particle 3 holes. That's the fact that it's a good approximation. That's the meaning. This equation? So, like the expansion of these are mu, you mean?
No, no, I'm just thinking about psi naught is even
Okay.
just psi naught. So
Yeah.
psi naught is equal HT phi naught. Then I apply the Hamiltonian, not the transformed Hamiltonian.
Yes.
So this will be H psi naught equal E naught
Delta is 0, yeah.
plus some terms. So you say
There will be something in your correlation energy which is not resolved, but it's very small.
but then this will correspond to operators that are applied to phi naught that are beyond two particles to whole.
Yes, that will be the contribution to the correlation energy which is given by, so for particle for holes and higher.
And we expect that the amplitude of those contributions are small.
Exactly. Yes. Yes. Yes.
You show it this formula, but
No, 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 no. Like I showed it yesterday. So like no problem, no problem. I accept question on the whole lectures. Yes. So we can look at excited states in the oxygen chain. So as I said before, we want to start small. And so we can also look here at the effect of three body forces. So blue, two body forces, red, three body forces, and then we have experiment in black. And actually, you can see that in general, if you just consider two body forces, your spectrum is kind of more compressed with the experimental one, and you get, let's say, a decompression instead if you actually consider three body forces. For example, I think it's more clear here in the case of oxygen 18, for example. And actually, in this case, yesterday I was mentioning this Berggren basis, which can be used to calculate states in the continuum, as it has some orbitals which are actually continuum single particle states. And everything that it's calculated here, let's say, covered by this these gray bands is actually in the continuum. And you see that they are kind of different, but because, okay, they are like in the theory, we are considering the threshold according to that theory. And so if you just consider two body forces, your threshold will be here. If you just consider three body forces, your threshold will be here, and so on. While here we have also the experimental one. And we kind of see that with free body forces, we kind of get a good threshold. Okay, 2+ excitation energy in calcium-48. So the importance of 2+ excitation energies is connected to the fact that they are usually a proxy to understand if your nucleus is a doubly magic nucleus. And so if it's an actually closed shell nucleus. So one usually looks at binding energies, separation energies, charge radii, and also 2+ excitation energies. And actually here in calcium-48, if we look at like the isotopic chain, we see that there is a bump in the 2+ excitation energy that indicates that we actually have a shell closure corresponding to calcium-48. And this has actually been used in order to prove, let's say, that nickel-78, so we are actually very far away in the neutron-rich land if we follow, let's say, the nickel isotopic chain. It's a nucleus that has 50 neutrons and 28 protons. So we are we are really in the neutron-rich land. And so, like in 2016, with couple cluster, the excitation energy of calcium-48 was used in order to get a prediction for the excitation energy of the 2+ state in nickel-78. And so here you see with crosses, we have different predictions for different chiral effective field theory interactions. We know very well what is the excitation energy of the 2+ state for calcium-48, and so we can exploit this correlation between these two quantities in order to get a prediction for nickel-78. And so here, if we then compare this prediction to the 2+ energies in the neighboring isotopes, we actually see that in the case of nickel-78, we have a bump. And so we can say, okay, we are in 2016, and we say, good, I think nickel-78 is in the neutron-rich land, but it's a doubly magic nucleus. And actually, a few years later, there has been an experiment on measuring exactly this energy of the 2+ state for nickel-78. And you can actually see that also in experiment, like the result of the experiment is this work. So it's this star that you see here at neutron number equal to 50. Also in experiment, we actually see this kink. So this was actually verified by measurement. And in particular, you see here different theories which are compared to each other. If we focus, for example, on a couple cluster, we actually see that we are very close to the 2+ and 4+ states here we have a good agreement with experimental data. And this is actually, I think, a nice story because it shows that, okay, theory at the time could do this calculation. And so it says, okay, this is like a doubly magic nucleus. And then experiment comes and can actually confirm this prediction. I think this is one of the things that I like the most about nuclear physics, is that you can actually see your calculations and compare them with experiment. And just, let's say, as many body nuance, one can also look at what is the effect of triple corrections if we include triples. I think I mentioned this yesterday when replying to a question, so I just wanted to show it. So here you see the spectrum of a very heavy nucleus, actually, 18100. And you can see what is the effect of going from CCSD in the calculation of various excited states and a calculation in which we also add triples. And we see, as I was saying before, there is kind of a lowering in the excitation energies, which is due by adding triples. Also, this is something that I wanted to comment on because there was a question yesterday regarding BOV2 transition strength. So BOV2 transition strengths are actually just transition probabilities going from like a zero plus state to a 2+ state, or we can see it also in also vice versa. And these are transitions which are moved by the quadruple operator. And so just focus on the experiment, which is the black here. Here we are considering mirror nuclei with different, so it means they have the same number of particles, but different numbers of protons and neutrons. But the idea is that just compare the experiment, which is black, with the ab-initio curve from IMSRG, which is the blue one. We actually see that we are not really able to reproduce these experimental values for the BOV2s. And actually, the solution that has been found to this problem was actually to introduce deformation in our reference state. So up to now, I presented to you results in which we are just using a spherical R3 Fock state. But we can also think, OK, we break rotational invariance, and we work with an axially symmetric R3 Fock state in order to be able also to model the formed nuclei. And so if we do this, if we introduce this kind of freedom into our many-body method, we can actually get a very good reproduction of the BOV2 values, which are here given by experiment. And here you have different theoretical predictions from coupled cluster using different interactions, and we actually get them whole very well. Okay, electric dipole polarizability. How much time do I have? Like 10 minutes. Okay, so this is actually the last thing I wanted to touch upon. So the electric dipole polarizability, as I explained at the beginning, depends on the nuclear response function. And the nuclear response function is characterized by the fact that we are basically looking at all the possible final states that the nucleus can reach via electromagnetic excitations. And so these states can be like in the bound spectrum, but they can also be in the continuum spectrum. And so we need a way to deal with it in our many-body method. Actually, I will not say much about that, and I will refer you to the talk by Miriam tomorrow that will explain to you actually what we do to deal with the continuum. So let us go to nuclei that we kind of know very well. So here you see the electric dipole polarizability of calcium-48. Here in this figure, I kind of put together everything that we know on it. So you have the experimental value, which is the blue band. This is like the first prediction that was given in the paper where that I discussed before about radii. This is like a prediction that was done at the CCSD level. But later on, it was possible also to introduce triples. And so you see that in general, we are getting lower values of the polarizability with triples, and we are getting also with different interaction in better agreement with the experimental data. Also here you see predictions from energy density functional theory, so a different approach, but still we get quite a good agreement between the theoretical approaches themselves and also with the experiment. If we look at the effect of triples on radii and the polarizabilities, so this is the case of nickel-68. So also here we are quite in the neutron-rich land. 28 protons, 40 neutrons. You see in this, on this axis you have the polarizability, on this axis you have the charge radii, and actually like the solid lines are, the solid crosses are predictions with triples. The dashed ones are predictions with CCSD, so just singles and doubles. We see that the results are going down, let's say, are preferring, let's say, lower values of the polarizability if we add triples. And this is, let's say, also leading us in better agreement with the experimental data. I just wanted to discuss Illumate because this is something that came out during the questions, and so maybe I was referring to something that not everyone is familiar with. So these are predictions that we made for the polarizability of Illumate. You see here that is plotted as a function of excitation energy. So the idea is that, as I was showing at the beginning, alpha d is proportional to the integral in the e to the minus 1 RE. So the inverse energy weighted integral of the response. Here we should integrate from 0 to infinity. This infinity is probably, let's say, the breakdown scale of chiral EFT. But here, since we have data only up to 20 MeV, I'm just plotting basically the integral from 0 to epsilon, to the epsilon you see in the plot. So basically, we are looking at how the integral builds up with excitation energy. And so we have calculation with a bunch of different chiral EFT interactions with both coupled cluster singles and doubles and triples. And we see that triples are bringing up the value. But if we add the experimental data, we actually see that there is quite a big discrepancy here. We are getting probably to 2/3 of the experimental value at 20 MeV. So why do we actually see this discrepancy coming out? I wanted to make a point here regarding the role of possible missing higher order correlations, because in the case of Illumate, we can actually compare our coupled cluster calculation with a no-Korshell model value. As I told you yesterday, no-Korshell model is an exact theory because we can get up to a-particle A-hole excitations. They also have some uncertainty given by convergence, but still they have in their framework more correlations that we have. If we get 1 interaction. In this case, it's, I think, NNLO SAT. They get this value, 0.44. Compared to coupled cluster, this is 0.37. And so this difference, which is almost 20%, it can be an indication of the impact of higher order correlations in our prediction. Still, this is not enough to actually explain our discrepancy, but one possible driving reason is actually given by 4 particles per holes. So this is very preliminary, but I'm showing to you also the quantity that Nakamura-san was showing before, so the dB1 in dE. So the experimental data corresponding to the ones you saw for the polarizability are here plotted in yellow. And then let's say this bunch of colored curves, it's just, let's say, a measure of our uncertainty when we get the response. This is something that you will hear more in Miriam's talk. And you can see that actually we lose some strength here at low energy, which is actually the point in which the polarizability is getting the more contribution, because we have this inverse energy weight. So it means we are losing this strength. It means we are losing something at the level of the polarizability. But it's actually very interesting to see that at higher energies we are kind of in very good agreement between 5 and 10 MeV with with the experimental data. And also, like we were discussing before with Nakamura-san, how can we relate this plot to what we said before with regarding, let's say, the having like neutron skin or a halo in illumate. How do you think this can be related? It's actually something open for discussion. So, if
This looks very much how you have for the correlated neutrons, the vision of the energy about 1 or 2 MeV. Maybe this part is missing, because I believe in the calculation you do to have these 4 neutrons going together in a correlated way is very hard to get.
Yeah, this peak, yes.
Because you could compare, I mean, it looks like, you see, look, the peak is about maybe 1 or 2 MeV,
Yeah.
2 MeV after the threshold.
Yes. Yes, this is a point where, like, more correlations are needed. Yes. Yeah, this can. Yeah. Yes, maybe like this is something that we can take during the questions. I just go on and finish here. So coming back to the case of calcium, so here I'm showing some predictions that we made for the case of calcium-40, which was recently measured via proton inelastic scattering. So the experimentalists measured the polarizability of calcium-40. Here we are showing it as a function of the polarizability of calcium-48. And so you see the color crosses are coupled cluster, the ellipsoids instead are energy density functional theory, and we have that these two observables are pretty much correlated between each other in both approaches. And moreover, what we see is that there are energy density functionals and coupled cluster interactions and chiral EFT interactions, which are able to reproduce both the polarizability of calcium-48 and the polarizability of calcium-40. And so we can think, okay, we can use these chiral EFT interactions, which are able to reproduce these polarizabilities in order to let's say, calculate the symmetry energy of the equation of state and see which kind of constraints we get from that. And here is what you see. So in the case, the constraints from chiral forces are in blue. You see always they are kind of preferring lower values of L. And in red instead, you see the constraints from energy density functional theory. It's actually very interesting to notice that there are two sets of energy functionals. So one which is fitted on the polarizability of lead-208, so this is the one fitted on the polarizability of a lead-208, the etched band, and the other one is not fitted on the polarizability of lead-208. But if we include the polarizability of lead-208, we are actually here restricting the range of allowed values. And also in this case, we are preferring lower values of the slope parameter. And here I'm actually comparing these constraints to like available constraints in the literature. So these first two, range 1 and range 2, come from like a review from Jim Latimer. And what he did was to take, let's say, all the data that we have for the neutron skin of lead-208, the neutron skin of calcium-48, make sort of an average, and look at what this would mean at the level of J and L. And this is actually range 1. Instead, if we consider only parity-violating elastic electron scattering experiments, one would obtain range 2. And so slightly higher. Drischler et al. Is a nuclear matter calculation employing one interaction, but with a very precise Bayesian uncertainty quantification related to the truncation of chiral EFT. U et al. Is the work that I showed before for lead-208. And Essig et al. Instead is the work I mentioned before, which included Ingo, which is, yes, coming from a Gaussian process model of DOS constrained by chiral EFT and astrophysical observations. We see that in general, all these constraints are preferring lower values of our slope parameters, so lower values of the pressure, of pure neutron matter at saturation densities. In particular, the constraints from the polarizability points to smaller values of L with respect to the Pyrex constraint. And this is something that, without, let's say, more precise data on the neutron skin of lead-208, cannot be really understood. So, an eye to the future. So, we actually made a very good progress in ab-initio theory in the last few years. Actually, this is a work which is not cluster. This is in medium SRG and valence space in medium SRG. They calculated 700 isotopes going from helium up to iron, and they gave, let's say, and comparing, let's say, their theoretical predictions from for separation energies to experiment, they give probabilities for the existence of neutron-rich nuclei on this side here. For example, in the case of calcium, they predict calcium-60 to be bound, but there is also like around between 0.4 and 0.6 probability of calcium-70, for example, to be bound. And this is a nucleus that potentially in the future could be measured at radioactive ion beam facilities. But there are also still challenges, there are still problems in nuclear structure that I find very interesting. So this will be like a personal opinion on what we should look at. Probably like if you ask a different nuclear theorist, they might give you a different answer. But actually, one example of an interesting challenge that we have ahead of us is a microscopic understanding of nuclear reactions. So the plot that you see here come from Nature Communications. It is a prediction of the deuterium-tritium fusion, which is actually the nuclear fusion process, which is more promising for future nuclear fusion reactors. And this is a prediction for the reaction rate of DT fusion into plasma. Of the reaction rate of fusion into like the DT plasma. And basically, people from ab-initio, using an ab-initio method which is based on the Nokorshel model, they predicted this reaction rate in the presence of a polarized and unpolarized DT plasma. And what they found is actually that this cross-section increases when we consider a polarized deuterium-tritium plasma. And this could be something interesting, let's say, for future applications, and actually shows also like the power of the ab-initio approach in actually looking at also processes which can be relevant for societal applications. And we want, and this is at the moment only possible for light nuclei. With this method based on Nokorshel model, probably we can get to A equal to 15 if we really push it at the moment. But I think it's really an interesting challenge for us ab-initio people to start looking at reactions in the medium mass and heavy nuclei. And with this, I thank you for your attention. I'm happy to take questions, comments. I leave here my email. Yeah.
So thank you very much. Okay, almost lunchtime, but so do you have any question?
Thank you very much for a very nice presentation, actually very nice lecture. Maybe very naive question.
Yeah.
Is it true that your calculation is rather dependent on the reference Hamiltonian?
Yes. Yes, there is
see.
a dependence on the Hamiltonian, depending on the observable. Like if we look at the polarizability of illuminate, yes.
I see.
Like it's 20%.
So for instance, okay, if you would like to see the halo effect, there are many Hamiltonians, like three-body Hamiltonians, three-body theory, like Hagino-san theory. Can you start use that kind of reference Hamiltonian? Because then you can probably mimic more the halo state, I thought.
So it's the same Hamiltonian that Yama-san was using?
No,
No.
like a three-body theory, like.
But it's like a cluster, like.
Yeah, cluster-like theory.
Okay,
like helium-6 case, alpha plus 2 neutrons.
Okay, in our case, we are like our method is based on protons and neutrons as degrees of freedom. So the calculations that I did were done with A equal to 8.
Okay,
so, like, for this kind of cluster problems, probably other methods are more suited at the moment, like few body methods, like what Chen was mentioning, the hyperspherical harmonics. This can be, I think, like a better framework.
Because what I thought is this missing strengths in helium-8 could be actually a kind of halo effect, I think.
Yeah, like in this case, like the interpretation that we give from like a many-body point of view is that we are missing higher order correlations. Right. So we don't have a pure four-particle four-hole excitation in our framework, and that is what I think is missing here, and what also, for example, the A-particle A-hole calculation that we have available is indicating.
Thank you.
So, any other question? Okay. So, all people must be hungry. So, okay. Yes.
Yeah, there's a related question. So, can you go to this B1 strands for helium-8?
Yes. This is preliminary,
I like to see it. So for the experimental results, the two peaks, is it related to 2-neutron breakup and 4-neutron breakup?
So like the data actually include 2 neutrons and 4 neutrons. Like we were actually discussing before if this is like how can we interpret this in the picture that we saw before in terms of neutron skin and halo, because we actually see like this first peak, which could be like the halo, and then we see like, I don't know if this is like a pygmy dipole resonance. It's kind of broader with respect to a usual pygmy dipole resonance. So, yeah, it's up for debate, I would say.
Yes.
You have a piece of information that is important. You change the scattering lane, the neutron-neutron scattering lane, and you have no effect.
Yeah.
You mentioned to me.
Yes.
And that means that, of course, you are missing some neutron.
Yeah, but here was looking at the data. I like at the data, and just if we aside from like the theoretical calculation, but if we look at the data and we try to map this into like halo or neutron skin structure, so as Nakamura-san was showing before, we have like this peak at the beginning, which is something that happens when we have halos, and then we have also like kind of a broad pygmy dipole resonance, but it's broad. So,
But in this energy region,
yeah,
already you have the helium-8 breakup in 4 neutrons and
it should be like around five, I think. Yes, around 5, 10. I don't remember the exact value. Yeah.
Yeah, can I understand it in this way? So you have a E1 operator that's operating on the proton itself, right? So basically, for the peak or this major regions, it's like exciting a proton. But for this halo regions, you need to excite an alpha particle. So if you don't have enough 4 particle 4 hole in it, you don't excite the whole thing. So you
Okay.
might missing some of those strands.
Yeah, this might be, yeah. To put the 4 particle for holes? No.
Yeah, I had a follow-up question on it. So maybe like to all three. It's like for Hale nuclei, like this DB1DE, you know, like the position of the first peak is kind of related to the separation energy, right? And I was wondering if, you know, even if that case, if there were like a 4 neutrons, like if the position of the first peak should also be related to a good reproduction of the separation energy of the state, because like so DB1D actually like they're very peripheral, so if you reproduce well like the separation energy in A and C, like the short range, like the low energy physics should be well reproduced. And so here I was wondering if, you know, what there are like multiple neutrons like outside of the core, like should we expect this behavior too or not?
Yeah, actually, for the 2 neutron halo or even 4 neutron, it's very difficult, but some relation exists to the separation energy. But compared to 1 neutron separation, 1 neutron halo, it's more complicated, I would say.
Any other question?
what is the difference in energy between you breaking in helium-6 and 2 neutrons to helium-8?
So il breakup in helium-6, it's 2.11. And helium-4, I think it's 4 MeV or something like that.
You have one peak at 4, you see? And then you have a lower peak that is where?
Yeah. Yes.
So this is the helium-8 breaking up in helium-6 and 2 neutrons.
The first peak, yes. Yeah, it's at lower energy with respect to the 4. Yeah.
The second peak is just the illuminate breaking in an alpha until the information.
Yes, there is, yeah.
Exactly 2 peaks.
Yeah.
Beginning and then,
Yes, yes.
okay, so you have an effect. But changing scattering length do not change the physics.
So the scattering length is a parameter which is used to fit the nuclear interaction.
Yeah, I know.
Yeah.
But artificially you could change it.
Yeah, like we have to refit the nuclear interaction at that point, yes. Yeah. Yeah, if I just plainly look at the neutron-neutron scattering length for the Hamiltonians that I used, there is no correlation with the value of the polarizability.
Yeah, because you are missing correlation.
So, and I have a question. In the same, so that this kind of calculation, and is it possible to calculate as a boron 19? Because also experimentally, they have this kind of data.
Boron 90 is a
Yes.
bit difficult.
Oh,
Because
why so?
like in, so like, this is like, Gauss cluster is simple when we consider closed shell nuclei and closed subshell nuclei.
Yes.
To get to open shell nuclei, we need to complicate our method a bit. We need to break rotational invariance and perform the calculation, which then at the end we have to include projection. There are additional challenges related to describing odd nuclei. So it's possible, but yeah, a bit more difficult than
Okay.
Illumate, definitely.
Okay, I see. Yeah, because so the number of
Yeah.
Newton is so larger, then
Yeah,
the
yeah, yeah.
calculation might be
Yeah.
possible. Okay, I see. Another difficulty. Another question? Okay, so sir, if not, so thank you very much for the Francesco.
Thank you.
Okay, 2 p.m. Okay, so in the next session we start at 2 p.m. Okay.
Francesca, I put you after the coffee break, but you are student to talk. Because I thought was more related to